Welcome back to BIOL105, Humans and the Environment. We're in Chapter 17, Waste Management. Here's a look at our learning objectives for this chapter. And again, if you want to print off the notes and follow along, that'll help you get less bored as you're listening to me talk. This is a great video about the life cycle of a can. An aluminum can is incredibly difficult, or it requires a lot of energy to make one aluminum can, so that's why the benefits of recycling aluminum cans are great. You might notice that's why you get the most money for aluminum cans at recycling centers. So I'd encourage you guys to watch this video on your own and recycle. So the cost of a can, the first step in making a can involves mining aluminum from tropical soils, and they get the bauxite out of this aluminum mine. And bauxite is generally strip mined in a process that permanently removes forests from large tracts of land. In addition, this bauxite aluminum mining often results in water pollution and acid mine drainage. In a second step, the bauxite is then refined into alumina, and this process uses thousands of gallons of water and produces a toxic slurry waste called red mud. Then there's a third step where the alumina is then smelted to remove anything metallic. And this process uses a large quantity of electrical energy. And finally, aluminum are heated and rolled into aluminum sheets, which can then be shipped to manufacturing plants to create cans. So this whole process of creating aluminum for aluminum cans can be greatly costly and using a lot of energy. But if we skip the refining and smelting stages, it would save about 10 billion kilowatt hours of electricity each year, which is an amount equivalent to the electricity used to power over 600,000 United States homes. So this is why you should really think about recycling everything, but especially aluminum. Here's a look at how aluminum is concentrated in tropical soils as bauxite. In letter A, the bigger picture, bauxite, it shows how bauxite is refined to alumina in facilities such as this one in Australia. Letter B shows the smelting pots where oxygen and alumina reacts with carbon electrodes that carry a very high electrical current, producing carbon dioxide and a pure aluminum metal. And then in C, each ton of aluminum then requires a great deal of electricity and nearly half a ton of carbon electrodes as it goes and is formed into sheets. So offering a cash redemption value on cans encourages recycling. That's what we do in California. So whether you donate your aluminum cans to someone who needs them or what, just please recycle aluminum. So let's talk about linear versus circular product life cycles. And we'll talk more about this more towards the end too. But in a linear product life cycle, waste is discarded at the end. So everything's linear. It's mined, it's made, it's used, and then disposed of. But in a circular cycle, efforts are made to use that waste instead of discarding it. So in the case of aluminum cans, it's mined, it's made, it's used, and then it's recycled, so we can skip the mining and making of the aluminum itself. So as we're looking at waste management, we're looking for ways to keep things in a circular process to manage our waste, because waste is a huge effect on the environment, as you all know. So this takes us first to our first part of our notes. Municipal solid waste refers to materials that are discarded from homes, businesses, and institutions, such as hospitals and universities. So the quantities and composition can differ where you are in the world. It can include paper products, yard waste, food scraps, plastic, metal, rubber, and cloth. And there's been a large increase in per capita production of MSW in recent history. This is a look at municipal solid waste and income. So you can see where, depending on if you're a low-income country or a high-income country, what makes up the majority of your solid waste materials. Organic material is the highest segment in low-income countries. That probably includes plants, food waste. In high-income countries, it's still organic material, but you notice that paper has a much bigger role in creating waste. Here's a look at how waste has grown. The amount of waste produced each year around the world is predicted to increase over time, but as countries develop efforts such as recycling, the result is less waste per person in some parts of the world. The production of waste in high-income countries is projected to decline greatly. Even though the growth in population increases, the production of waste is predicted to decline. Sanitary landfills, and this takes us through still in our first section under sanitary landfills. I skipped one in your notes under municipal solid waste. You'll see number 1, the quantity and composition of solid waste differ from region to region and have changed over time. And then here we look at modern sanitary landfills, which is your next bullet point in your notes. These are designed to prevent 4 important problems associated with waste dumps: the accumulation of methane gas, which contributes to carbon in the atmosphere, the contamination of groundwater, odors, and the reduction and control of pest species that can also be disease vectors. So we're going to look at what a sanitary landfill looks like. It's lined with impervious clay and plastic to prevent leachate from getting out. And leachate is under your blank in number 2. That's water percolating through accumulated waste, can pick up a variety of toxic chemicals called leachate and can contaminate the groundwater. So if we line the landfill with impervious clay and plastic, that leachate cannot get through. The trash will be compacted and covered. When it's full, it's capped with clay, and usually then grass or a park or trees are built on top of it. Methane is usually produced from the waste, and it could be a source of green energy later. So this is a look at a sanitary landfill. You can see how the clay surrounds the outside to prevent anything from leaking through, and then you have the compacted solid waste. You have the gas recovery system shown there to capture methane gas to generate electricity. And again, when the landfill is full, layers of soil, sand, and clay seal in the waste. And you can also see here how wells and probes are used to detect any leachate and methane leaks. And leachate is regularly pumped up to storage tanks for treatment and safe disposal. So this is what a sanitary landfill exists, where most of our trash is going when it gets picked up on the side of your street. Waste can also be incinerated, and this includes burning it at high temperatures to reduce volume and weight. The volume is only about 5 to 6% of original waste, so that would just be the ashes that are left. And facilities use filters and scrubbers to reduce emissions of pollutants. Some can harness this heat for electricity generation, and we call these waste-to-energy facilities. So here's a look at a waste-to-energy facility. You can see the truck coming in, bringing in the waste, and then taking it into the boiler where it's being incinerated. And the hot gases or steam are used, first of all, to be cleaned. So they're being removed, the toxins and pollutants. The water vapor is cleared and leaves as gas, and the steam will power a generator or a turbine, which produces electricity through a generator. So this is a waste-to-energy plant. Industrial solid waste includes all waste generated at each stage in the manufacture of products. So an example of this would be waste from making aluminum cans. So this is your next blank in your notes under letter D. In the US, 7.6 billion tons of waste is produced per year. Some ends up in industrial waste facilities, some ends up in municipal landfills. And industry especially seeks ways to reduce, reuse, and recycle at every stage of the production. And yeah, that next blank, number 2, in contrast, it's usually collected and managed by the private sector. So municipal solid waste that we get picked up on the side of our street is managed by city and county officials. Usually each city has a different waste removal system, whereas industrial solid waste generated by facilities, is usually taken care of by the private sector. And 7.6 billion tons is your final blank there of waste produced each year. Then we get to hazardous waste. So this is the top of your next page. Hazardous waste includes anything that's flammable, corrosive, explosive, or toxic. The EPA identifies three categories: source-specific, which are unique to particular industries; non-specific, produced by common manufacturing and industrial processes, such as cleaning and degreasing solvents; and then discarded commercial chemical wastes, which includes any products such as unused paint, pesticides, and pharmaceuticals. So the US EPA, and again that's the Environmental Protection Agency, maintains a list of the kinds of household hazardous waste. It also provides information on waste characteristics and appropriate means of disposal. So this is a little project for you to do. If you can identify 5 containers of materials that qualify as hazardous waste in your cupboards, your basement, or your garage, what specific threat does each type of waste pose? These wastes are typically managed by individual counties, and each county lists its procedures for hazardous waste disposal on its website. So take those 5 containers that you found of hazardous waste in your homes and think about where you would dispose of them. Not in your regular trash can, but maybe you'll take it to a place like this. Usually there are hazardous waste collection kind of drive-throughs where they'll take the hazardous waste directly out of your car. I've been to one, I think in Downey. So these happen throughout the year periodically. All right, so as we look at more hazardous waste, the current methods of disposal include permanent retrieval storage sites, which is your blank under number 3. And these are just monitored to ensure no leakage into the environment. And then in bioremediation, this is where we have living organisms such as little tiny microorganisms breaking down hazardous waste into harmful components. Other methods of disposal they need to be chemically processed, high temperature incineration, so they're burned, or Superfund sites, and we'll talk about what those are. Here's a look at what bioremediation is. This is showing in 1889, workers spraying nutrients to encourage the growth of oil-devouring microbes on the shores of Prince William Sound. And this area was polluted with an oil spill from an Exxon tanker back in 1989. And Prince William Sound today, you can see what it looks like there. So bioremediation worked. Those little microbes were devouring all the oil. Biomedical waste, then, we'll move on to this. This is waste produced in huge quantities from hospitals and medical facilities. It can be solid waste, it can be hazardous medical waste, or it can be radioactive waste. So this is biomedical waste is your first blank under letter B, biomedical waste. Also, biomedical waste, it can spread infection, disease, or decompose and produce toxin or odors. That's because it can include human, animal body parts, tissues, blood, and used medical instruments. So you'll see these in your probably doctor's office when you go for a checkup. It's a familiar sight. It contains all the sharps, such as this. They're designed to collect needles and other potentially infectious items that will usually have some sort of bodily fluid inside of them. Then we get to electronic waste, which is also known as e-waste. The regulation of this is only recent because electronic waste has increased greatly over the years. It can include old televisions, computers, cell phones, and other electronic devices. Broken or obsolete electronics may contain heavy and precious metals, but the recycling of these is less than 20%, so people really aren't recycling their electronics. The US doesn't have national regulations on this. I think it's a state-by-state run thing. The European Union and some US states have take-back regulations where manufacturers must take back the product at the end of the life cycle, which is a step in the right direction. Here's a look at the amount of e-waste generated. So again, this is electronic waste in 2014. What's the biggest sector? Small equipment such as shavers, microwaves, toasters, or video cameras. The next one up is large equipment like electric stoves, washing machines, and not far behind that we have temperature exchange equipment like fridges, freezers, and air conditioners. Here's a look at workers in Asia reusing and recycling parts from electronic devices that have been discarded in developed nations. These activities expose the workers to many toxic substances because, again, electronic waste can have some of those heavy metals. Radioactive waste, then, is our next blank. This requires long-term monitoring to avoid human health risks. We can have low-level radioactive waste, which contains comparatively low amounts of radioisotopes. This is where we have the greatest volume of radioactive waste, and this usually comes from hospitals and different science labs across the country. Or you can have high-level radioactive waste, which is the most dangerous, and we store that in what we call fuel rods. So number 3 and 4 in your notes under radioactive waste are low-level and high-level radioactive wastes, with number 1 being long-term monitoring. Storing low-level nuclear waste. This storage area holds barrels of low-level nuclear waste. All components used in the nuclear fuel cycle must be disposed of properly according to their level of radioactivity. Here are the storage sites for high-level nuclear waste. It's stored at nuclear facilities across the United States. At first, the spent, that means used, nuclear fuel is stored in pools of water, and after the fuel has cooled for many years, it may be transferred to dry storage casks. So you can see we have a few in Southern California. You'll see a lot of these storage sites on the East Coast where you have a lot of industry and labs. So you'll usually find these in larger cities where they're doing a lot of radioactive, either with their hospitals or science labs. Sustainable waste management. So we'll kind of finish this chapter talking about how we can sustain our waste management as it continues to grow. There's multiple strategies, and I'll go through all of these in order. There's 5 of them. They're listed all on your notes there. They kind of take up the end of this page and the beginning of the top of the next. The first one is what we call preventing waste. So consumers can avoid relying on waste, such as disposable bottles, diapers, and razors that are not designed to last beyond a single use. So you can try to create alternate buying patterns and buy things that are not disposable but are reusable. Reducing waste. Major retailers are beginning to put pressure on manufacturers and suppliers to reduce packaging waste. Walmart, for example, has reduced plastic shopping bag waste by 38%. As you know, back in 2016, the governor issued no more plastic bags in California. I think he currently has suspended that for 60 days as we're going through our pandemic. But reducing waste, an example of that is getting rid of plastic shopping bags. Reusing waste. The EPA estimates that about 2 to 5% of the material sent to landfills is actually reusable, including clothing, furniture, and building materials. So donating to Goodwill, Salvation Army, things like that. These are some methods for dealing with waste. Some are more desirable than others. The waste management hierarchy shows the most preferable options at the top. As you work your way down the list, the options become less and less desirable for the environment. So if we finish up, then we have recycling waste as our 4th option number down, letter D in your notes. And we'll talk about closed loop and open loop recycling, which are your 2 blanks in there. And then we have energy recovery and disposal as your final 2. So as you look at this, the best one for the environment is just to prevent waste to begin with. I don't use cloth diapers. I probably should after teaching this class. But any way you can prevent waste, not using plastic bottles, but a reusable water bottle, reducing waste itself, donating it, reusing it, and then recycling it. Considerable amounts of economically valuable material that enter the waste stream are retrieved for reuse, and such trash picking is estimated to add nearly $1 billion to the U.S. economy. So people will actually pick through trash. That's actually helping sustaining our waste management goals. So these are our final: diminishing the waste stream, finishing up your notes. Recycling saves resources and energy, and we have closed loop and open loop. We'll talk about the difference between those again. Energy recovering is taking the waste and burning it for energy or other means. And then disposal is the final option that we want to use. Garbage trucks will crush that garbage, and then that'll save space as it puts it in a landfill. Here's US recycling rates since 1985, so it's great to see that they've increased so much. This increase is a result of growth in the technology and infrastructure to actually support recycling and creating correct waste management systems. In addition, many communities have mounted programs to encourage recycling, such as many states and cities that give you money back for your cans and other incentives. So closed loop and open loop recycling. An example in letter A is showing closed loop, showing how the aluminum in cans can be recycled to produce new cans. That's a form of closed loop recycling where the end product is constantly being reused. The wood-like in letter B, the wood-like boards in this park bench are a composite material made from recycled plastics. And that's a form of open loop recycling that leads to a different use of the recycled material. So closed loop recycling, the same materials used over and over again, such as in aluminum cans. In open loop recycling, waste products are used to create an entirely new material or product, but it's still a type of recycling because you're reusing one material and ending up to being another material. Challenges to municipal recycling. And let's see here. These challenges, I just have a little note for you there. Markets for recycled materials, there's still such a consumer demand for them. The cost of disposal, and it's good to just be honest about it. It might actually be cheaper just to dispose of these materials than recycling. And the government policies for resource extraction industry and what those might include. Challenges of recycling. Local regulations and situations influence recycling worldwide, as you know. For example, there's no strong relationship between recycling rates and income across 30 different major cities. Even some high-income cities have low recycling rates. Horizontal lines on this graph represent the averages for each income level, and note that not all city names have been shown for the sake just of simplicity. But this is just showing the recycling rate for 39 cities by income level. And you can see it doesn't matter, high income cities between San Francisco to Buran, they can have low or high recycling rates throughout the world. So it doesn't matter really your income, it just matters how well the policies are put into effect to increase recycling rates. So what can you do to reduce your waste footprint? Ask yourself these questions. Do I really need this item? Was it sustainably produced? Can I reuse or recycle this item? Will I actually recycle it? And can this item be safely discarded without risk to the environment or human health? So just questions to think about before you buy anything. The life cycle assessment brings us to our next set of notes under number 17.4, the managing product life cycles. So this is your first blank in your notes, number 1. This is a method used to evaluate the environmental impact of a product throughout all the stages of its life, from resource extraction to manufacturing, distribution, use, and final disposal. A complete life cycle assessment includes these components, and they're listed for you there and in your notes: inventory analysis, impact analysis, and improvement analysis. The inventory analysis analyzes the inputs and outputs of energy of that product, materials, and any pollutants. The impact analysis looks at the impacts in the environment, the economy, your health, social and cultural impacts. And then improvement analysis looks for opportunities to reduce said impacts, as listed before. The life cycle assessment, the full consequences of the manufacture, use, and disposal of a product, can be understood by a close examination of these inputs and outputs associated with each stage of its life, from what we say the cradle to the grave. So this is a look at the input, what is needed to create a product, the product stages itself, and then any outputs that come out of creating that product. This is showing the complex life. Greenhouse gas emissions is one measure of the environmental impacts associated with manufacturing, using and disposing of a typical cell phone over its life cycle. This is a life cycle assessment by Sony Corporation indicated that greenhouse gas emissions over 3.5 year life cycle of a phone are about 21 kilograms of carbon dioxide. So you can see here how it's incredibly important to recycle cell phones because they emit a lot of carbon dioxide as they're being created. In recent years, reimagining project life cycles, a variety of alternative approaches to product manufacture and disposal have gained recognition through industrial ecology, designing to mimic natural cycling systems, disassembly. So a lot of products are designed for disassembly at the get-go, making it easier to circularize and reuse some of the components, and extended product responsibility is where producers are responsible for the product throughout the life cycle and then they take it back once you're done using it. So these 3 blanks are the next 3 blanks in your notes: industrial ecology, designed for assembly, and extended product responsibility. This is a look for a group of team from Stanford University engineering students. They designed a laptop computer that can be disassembled in 2 minutes without any tools. The electronic parts that are shown in purple can actually be separated to go into an envelope for transport to a recycling program, and the remaining plastic and metal parts can be placed in ordinary recycle bins. So this is an example of a product that was designed for disassembly. Encouraging recycling, these is a look at just what you might see in our cities. They try to promote convenient and prominent disposal systems. And this is the foundation of successful recycling programs, is promoting and encouraging recycling and then having people actually go through and do them. In the US, the management and disposal of hazardous waste are governed by 2 federal laws. And those federal laws are seen there, the RCRA and then the CERCLA. So they fund Superfund sites, they have take-back regulations on electronic waste, and the Waste Tracking Act in 1988 helped to monitor biomedical waste. And these 2 acts are your final blanks in your notes: the Resource Conservation and Recovery Act, and then the Comprehensive Environmental Resource Compensation and Liability Act. And I just realized we skipped the last one, that is the Medical Waste Tracking Act in 1988. This is a look at what a Superfund site is. This is an old mine that's now closed, but the pollution in it remains. The company that opened the mine no longer exists, so the cleanup of this site is actually being funded by what we call the EPA Superfund. So a Superfund site is whenever the EPA, the government, gets involved to fund the cleanup of a particular site. And that finishes this chapter of Chapter 17. Thanks for listening, guys. Take care.